Welcome folks to the Northwest C++ Users Group meeting. A couple announcements real quick. First, in August, we are going to do our pizza feed. So plan is to not meet here. We're going to reserve a picnic shelter up at Grass Lawn Park, which is just up the street, and there'll be free pizza. So it'll just be a social meeting. We won't have a formal presentation that month. September is going to be lightning rounds. So anybody who would like to present and just do something short, we'll do that in September. Chris, I see you're online. Did you have anything you wanted to announce for conferences?
Yeah, CPP Con call for submissions is open for 3 more days. So, Sean, get your talk in.
Well, hold off till you hear it, and then you can tell me.
Yeah, then we'll say you should have held off a little longer.
That's right.
We'll put you next to last again.
Oh, please don't.
Well, you guys wanted to be together as a pair with David, so.
Yeah, the first was better. That had Dave wanting to rewrite the talk, so we spent the entire conference in the hotel room rewriting the talk multiple times. So going first would have been better.
Hey, does anyone have any other announcements for? Okay, with that, I'm going to turn it over to Sean Parent, Senior Principal Scientist for Adobe, and off we go.
Okay, thanks, Lloyd. So when Lloyd asked me to give a talk here, I had a talk already prepared that I gave at a meetup in New York about a month ago. And I asked him to choose between that talk and an idea for a talk, which is this talk. And he chose this talk. So this is the first draft of a talk. And I like doing meetups to kind of vet material. So if you want to interrupt me at any point and say, I don't understand or whatever, that would be helpful. Help me shape this talk, especially since we have a very small group here.
Forget about the same number online. So
about the same number online. Okay. So you'll have to relay any questions that come in online. This talk came about because of some comments in a conversation I was having with Dave Abrahams, which is, I read code and people tend to write code that ends up being very convoluted. And I said, if you just write code with value semantics, then everything gets easier, was the comment I kind of threw out. And he was like, yeah, but we don't really have language support for that. And so that makes it hard. And I was like, well, what are you talking about, right? You can write with value semantics in any language. And so that's where this local reasoning in any language came up. And so I had this idea kicking around to say I should just do a talk about how to write code that you can reason about simply in any language. The problem is in putting the talk together, you get hung up on so many of the details of C++ that this is going to pretty much fill an hour. And just talking about C++. So kind of cross out any language and we'll fill in C++. But the rules here and the underpinnings and the basic ideas apply to any language. Yeah, right. Hey, Mark, welcome. Mark Hamburg from Adobe is joining us. So I'm so the ideas in this talk I think map to any language, and I use some terminology that's not normal C++ terminology to try to abstract a little bit away from C++ conventions as we go. So what is local reasoning? Well, in very, terse terms, it's just the ability to reason about a defined unit of code, right? So as a standalone piece and be able to read through that piece of code and convince yourself, yeah, this code is correct. This code does what it's supposed to do. And so the scopes we're looking at when we're talking about a unit of code are two things in this talk. We're talking about functions. Right? Can you look at a function and reason about the function and convince yourself that that function is correct? without going and looking at all the places where that function is used or all the details about all the implementations of the functions that code relies on. And then we want to do the same for classes, right, as another unit. Can you look at a class and reason about a class and convince yourself this class is correct? So some terminology here. We're concerned with both sides of the API when we're talking about local reasoning. And so I'm going to use the term the client to mean the calling function or the code that's holding on to an instance of a class. And the implementer side to be the callee or the implementation of a class. I don't just use caller and callee because that doesn't work very well when you're talking about the class abstraction. So it's the client and the implementer. So let's just start with a very simple function. Got this function, void f. So what does this function do? Just from the interface. Anybody?
I'm a
You're a
You're a functional guy. So Mark's answer is going to be clearly nothing.
It could burn lots of CPU.
It could burn lots of CPU. Yeah. So either this function is going to do nothing or it's going to operate purely through side effects. Okay. And if it's operating through side effects, we've lost our ability to reason about it locally right up front. Okay. So the first thing we're going to say is we're going to try to avoid side effects. So let's put a specification on this function. It does nothing. Okay. So now we can implement it. And just at this level, I hope you're all pretty convinced that that's the correct implementation, right? We got a function called void. It does nothing. So let's make it a little more complicated. Here's a function that returns successor of x. Good. Yeah, we should probably have a precondition on here saying that x can't be max int, things like that. But it's okay, there is no successor to max int, so that's kind of implied. It's pretty good as it is. So let's talk a little bit about function arguments. Let's take that initial function, but we're going to do it now where we're just going to mutate x, upsetting Mark, our functional programmer here. So this increments the value of x by 1. So we introduced another precondition to this besides the overflow precondition. Anybody know what it would be? Guesses?
Reference has to be valid.
The reference has to be valid, yeah. So, yeah. No other thread of execution is accessing x during this operation, okay? There's no way for A here to test that. So the client has to ensure it. As soon as we introduce a level of indirection, in this case, passing the argument by reference, we're raising the prospect of aliasing in the interface. Having more than one way to access an object is what aliasing is. So the rest of this talk is really about techniques to control aliasing and confine the effect of an operation so that we can reason about it locally. Now, we certainly don't want to write preconditions like this on every function we write that takes a reference argument. So instead, we're going to develop a set of general preconditions that must be upheld for all operations unless otherwise specified. So let's start here. We'll have a general precondition. Arguments passed to a function by non-const reference cannot be accessed by other threads during the operation. And arguments passed to a function by const reference cannot be written to by another thread during the operation, unless otherwise specified. So that's going to be our general precondition to start. Seem like a good rule? Probably good. You know, if we allow race conditions, it's undefined behavior. Okay, so now we can get rid of that precondition. And now this function looks fairly simple, fairly easy to reason about. Okay. Now, let's take a look here. We've had two forms of this function, and there's a duality between these two forms. Okay, one is an action where we're modifying X. And we could always write something that's doing the modification in terms of a functional form, X equals f of X. Right? And we could write the functional form in terms of the action. So there's a duality between choosing these things. And for a given algorithm, one or the other of these may be more efficient. It's not guaranteed which one. You can't say always passing by mutable reference is more efficient. It's not. Okay. So let's expand our ideas about argument passing just a bit. We're going to say that we have let arguments. Typically, these are read-only arguments, so they're passed in by a const reference. We have in-out arguments, so that's what we just saw, our T reference. And we have sync arguments. These are arguments that can be consumed by the caller. And conceptually, they die from the callee's point of view, although in C++, we have a shell left behind that we want to either destruct or assign to. And we've got a little bit of a problem in that C++ overloads the syntax of tref to either mean an R value reference, or it can mean a universal reference if T is deduced. So if T is deduced and we want to constrain this to be an R value reference, we're going to have to add a requires clause here to constrain it, which is pretty ugly. Is what it is. Okay. So let arguments have the post condition that the client's value isn't modified. And in-out arguments have the post condition that the client value may be modified. And sync arguments have the post condition that the client value is assumed to be consumed. Okay. And the client value afterwards may be assigned to or destructed, but otherwise, as a general rule, we're not going to touch it. Okay. All of these come with the qualification unless otherwise specified. So let's look at a simple function here. We're going to expand our code that was incrementing, and now we're going to increment by a value. So we're going to take the value that we can increment, and we're going to increment it by n, our second value. Okay, looks like a reasonable function. We can all agree it looks fine. Now, what if this is called in this way? We have an integer of x, we offset x by x, and we print it. What does it print? Everybody know? Right. 2, we're going to increment it. So we're going to have x plus equals itself, 2. So it's going to print 4, right? Yeah, it prints 4. Okay, so what's the problem here? The problem here is we violated our contract. We said we weren't going to modify n, but we did. Okay, and we did say we were going to modify x, and we upheld that contract. Okay, so we modified x, but we also modified n. So our contract, when we pass x and x, is in contradiction here. You might think, not a big deal. We expected 4. We're big boys. We know what we're doing. So if we change the implementation of offset to be this. Okay. So we're just going to increment x by n each time through. What's that going to print? Yeah, it's not. Right? This is never going to terminate.
Yeah.
Okay.
Arguably all of your functions, because the overflow is just it panics and doesn't return. The conditions that, like, if it returns, it will have done this.
If it returns, it will have done this. Yeah. So yeah. But this one, there's only one value that we could have for x here that would terminate. Well, you know what it is?
I should have had.
Zero.
Yeah.
Zero works. Okay. So otherwise, this isn't going to print anything. Okay, so with 2, this is not going to print. Okay, now you might think this is a silly and contrived example. So what about this? We want to erase all the elements of our vector that match the first element. Okay, what does that print? Any guesses? Anybody think 1, 1?
Depends on the implementation of erase.
It does depend on the implementation of erase. So depending on your library, and there's an example on Godbolt. Okay, so it actually depends whether or not you're using the Clang standard library or the GCC standard library. I believe it's the Clang standard library that will print 1, 0. Welcome, come on in. Okay, everybody understand what went wrong? Right, so A0 is getting passed into erase by reference. And so we start and we say we're going to remove everything that matches 0. And so we remove the first element and we move a 1 into that first element. And now A0 is 1. So now we're going to remove the 1s forward. And so we end up with a 1 in the first slot, and then we remove any other 1s and we end up with a 0. Okay. So in, out, and sync arguments cannot be accessed except directly by the implementation for the duration of the call. Okay. So let arguments passed by reference cannot be mutated for the duration of the call unless otherwise specified. So this is an extension of our rule that we can't have aliasing across threads to say when we have an in, out, or a sync argument, a reference to our thing, we can't be aliasing it, period. Okay, not through another argument. Now, other languages, recent languages, have these rules kind of embedded much deeper into the language. So Swift has this notion of the law of exclusivity. To achieve memory safety, Swift requires exclusive access to a variable in order to modify that variable. In essence, a variable cannot be accessed via a different name for the duration in which the same variable is being modified as an in-out argument or a self within a mutating method. Rust has the borrow checker. Mutable references have one big restriction. If you have a mutable reference to a value, you can have no other references to that value. Okay. In C++, we have the same rule. Okay. It's just up to the developer to uphold it. Okay. It is nearly impossible to reason about a function in the presence of aliasing. You end up with very complicated specifications if you're trying to write a function that supports aliasing. And what the C++ standard says as far as the standard library goes, and as far as like our erase function goes, is in the presence of aliasing, the result is unspecified. It's not undefined behavior, but it is unspecified, which is pretty close. Okay, so 1, 0 there is a valid result per the standard. Okay, so that's function arguments. So let's talk a little bit about projections. Okay, so when we return here the successor of x, we're returning it by value. Our other functions, we're returning voids. Is there a time when we would want to return a reference from a function? Well, think of a use case. So I ask this a lot and people are like, no, I don't think you should ever return a reference.
I've seen it where you return a reference, so then like if you want to say chain, like you return a reference and then you call a method on that.
On the thing.
On the return. And then
Right, for doing chaining.
Yeah.
So operator equal is kind of a canonical example, right?
A sub 0 is basically you call the function to dereference into the vector.
A sub 0, right? Or in the standard library back, right? I can write this, I can say a dot back equals 42, right? Back is returning a reference to the element. And then if I print it, I've overwritten my back element. Okay, so it's actually surprisingly common that we actually do return references.
You could have a custom allocator instead of.
What's that?
You could have a custom allocator for one of your data structures,
Uh-huh.
new something and return it as a reference. It's not forbidden to do so. Syntactically convenient.
To return a reference instead of a pointer after doing an allocator? Maybe, I mean, so long as you have some kind of rules that can reason about that.
It's nothing for.
Oh, C++ doesn't forbid much.
It has all the memory safety of assembler.
Right. In fact, in doing this section, I mean, bringing that up, it raised a question for me, which is what is the lifetime of a pass by value argument? Can I return a reference to a pass by value argument legally is the question. And it turns out the answer is that it's implementation defined whether or not that works. Okay, and in Clang it does. In GCC, oddly, if I return a reference to the argument, it will give me a warning. It will compile. Clang will give me a warning also. The lifetime rules around the arguments are exactly the same as they are in Clang in GCC, which means they are treated as temporaries. So they exist until the end of the expression. So returning a reference would be valid. But Clang explicitly returns an invalid reference. It returns a reference to 0. Okay. So a nulled reference, which I thought was interesting. So they're allowed, it's implementation defined, do what they want. So projection qualifiers, right? So a projection here, I should have explained a little more. So a projection is a reference essentially to a part of some whole. Okay, and that could include the whole itself, right? That's the whole is a part of itself. So here, what we're doing is we're returning a dot back is returning a projection to the last element within our sequence. Okay, so we can think about projections as having qualifiers just the same way our arguments have qualifiers. Okay, so we can return a projection that's mutable that would allow the projected object to be modified. We can return a constant projection which doesn't allow the object to be modified. And we could return a consumable projection which allows the projected object to be consumed. Okay. It's relatively rare that you see the last form. It is allowed in the language. C++ allows a lot. But it's not a coincidence that these match our argument qualifiers. Okay. Because the argument qualifiers, you can think of those as being projections, right? We have functions that take projections as arguments. So when would you want to return an R value reference? Well, you can almost always get the same efficiency returning by value because of return value optimizations that go on in the language. But sometimes you might want to say, well, if this object is a temporary, so this is a member function signature here, and the ref there means that it's the object itself, that's, star this is an R value. Then I've got some method that wants to extract some piece of R. It's going to die, so go ahead and suck it out just before the object gets destructed. Okay, but usually what happens is we just end up returning a mutable projection, and then if we want to consume it, we do an explicit move on it. But that always requires some form of fix-up, right? If we extract some part of the whole, now we have to fix up the whole, right? So in this case, what we're going to do is erase, which causes the destruction of the move from object, right? So we can move out the back and then pop back. Really common pattern. Okay. So projection validity. A projection is invalidated when the objects they are projected from is modified other than through the projection. Okay, so if we have our vector A of 0, now P is a projection to the first element within our vector. And if we push back an object into that vector, right, our vector could resize, that invalidates our projection. Okay. This was kind of an odd way that my slide built out here. So here we have a vector and we get a projection to the last element in it, and then we clear the vector. That invalidates our vector. Another case here, we've got our vector, and again, we get a projection to the back element. And now we change at index 2, the third element, okay? E is not invalidated here. So our projections don't intersect. And then the other time it's invalidated is if the lifetime of the objects they are projected from ends, right? So in any of these cases, as soon as our vector goes away, we've got a dangling reference and we're done. And so that can happen. References can be lifetime extended, but only if they're direct temporary. So here, if we have a projection coming out of our vector, indexing creates a projection for the 0th element. It's a temporary vector though, so P gets created as a valid projection, but then immediately becomes invalidated. So you can't do anything with P other than let it destruct or have undefined behavior. So given that, we can now think about iterator pairs and views and spans are projections, gotta fix my wording there, of a collection of values. Okay. So, and they follow the same rules as all other projections, right? If we have a projection and our projection is mutable, then it can't overlap other projections. Okay, so if we do this, if we say copy begin A, so we're copying from the beginning of this, the first 2 elements of it, and we're going to write out starting at the first element. That's invalid. Our 2 projections overlap. Okay, but it is okay to do this, right? We can copy the first 2 elements into the second 2 elements. It's a non-overlapping projection. Now, copy itself has rules where if you were copying, this is copying right. If you were copying left and the projections overlap, copy explicitly says that that's allowed. But if you're writing your own code, this follows under the unless otherwise specified. And if you're relying on that behavior in your code, you better put a comment in that says, yes, these 2 things overlap, but I'm copying left. And so therefore, according to the standard, this is okay. Okay, so now we're going to talk a little bit about objects. Let's start here. Let's say I have this function. I've got a shared pointer to a widget P. What's my question? What is the type of the argument for F? Seems like a ridiculous question, right? I mean, clearly it's a shared pointer widget, right? I have it on the slide, okay? But is it? What is F operating on? Is F operating on the shared pointer? Or is F operating on the widget? So if F is operating on the widget, Is this a let argument? Is this a sync argument? Is this an in-out argument? I don't know.
Well, it depends on whether you, I don't use shared pointer much, but thinking about unique pointer, it depends on whether you want to modify the pointer or the widget.
Right, right,
So-
right. And this is
Also, I think
ambiguous.
it's a
And
shard pointer, so.
the shard pointer. Ooh. That's real fast.
Distributed systems.
Yeah, distributed systems should be shared, but okay, I will fix that. Yeah, so, but the call is ambiguous because if we were operating on the shared pointer, we're passing it in by value. We can't be modifying the caller side. Okay, so maybe we're passing it through and storing it somewhere. We don't know. Okay. So to understand F, we need to understand the extent of P, right? How far does P go? Is P the pointer? Is P the thing pointed to? If my widgets contain shared pointers to other widgets, very common thing, okay? How far does P go? What is my argument to F? That brings us to the topic of equational reasoning, and we'll see how this connects in a moment. Equational reasoning is proving that expressions are equal by substituting equals for equals. And that's how we explain how code works. And it's a component of building a larger proof when we're reasoning about code. To know if two values are equal, we need to know the extent of the values. We need to know how far they go. Okay. Now, equality, just as a reminder, is an equivalence relationship. It's reflexive, meaning that X is always equal to X. It's symmetric, meaning if switch to A and B, if A is equal to B, then B is equal to A. And it's transitive. So if A is equal to B and B is equal to C, then A is equal to C. And equality connects to copy, okay? Meaning that we assume that a copy is equal to the original, but disjoint. And that's logically just disjoint, not necessarily physically disjoint. What we mean by that is addresses may be shared, but under mutation, modifying the copy doesn't modify the original. That's what we mean by disjoint. So earlier we had put up this trivial transformations and actions and the duality between the two. Okay. This only holds if copying X, right, in the functional form, right, if modifying X through the action here would have the same effect as modifying X and then returning it. Okay. So for this duality to hold, in some sense, X has to be self-contained. So how do we do that? Well, a composite object is made up of other objects, which we call its parts. Now, the whole part relationship satisfies four properties. One is connectedness, which means that from the root, from your whole, you can get to all the parts. That's what connectedness is. One is non-circularity, which means an object is not part of itself. One is disjointedness, which means that an object is self-contained in the same way we just talked about being disjoint through copy, but modifying that object doesn't modify other objects. And the other is one of ownership, which is that the whole owns all of its parts. If it goes away, all of its parts go away. So that's the whole part relationship. Okay. So if we have a vector like this, then the elements of that vector, the integers 0, 1, 2, and 3 that are stored within that vector are parts of that vector. And if we have a struct like this, then name and int are part of that struct. Those are parts of the whole. So when we're passing objects to functions, we want to pass the narrowest scope. We want to pass the whole. We want the transformation dichotomy to hold if we're going to be able to reason about the code. If we're going to be able to look at this function and say, what's the extent of the mutation that's going to happen under here? Then we want to say we are modifying the widget P. Okay. Okay. And it should be possible to represent this with a duality form. We should be able to say, well, we can write a function f that consumes p and returns a new widget. Okay. Okay. So whole part relationships, but we're writing a program and other relationships happen in that program. Okay. We have other ways that things are connected. That's what we call extrinsic relationships. An extrinsic relationship is a relationship that is not a whole part relationship. Any relationship that is not a whole part relationship is an extrinsic relationship. So we've got our vector 0, 1, 2, 3. Okay. And there is an extrinsic relationship just implicit in here, which is that a sub 0 is before a sub 1. So relationships, extrinsic relationships happen all the time. Okay. Let's talk a little bit about relationships. A relationship is a connection between two elements in a set. That's the mathematic notation. A relationship between objects may be severed by modifying either object within that relationship. Okay. And a relationship may be witnessed by an object, which means that we can basically write down in code something that represents that relationship. A pointer or an index is an example of witnessing a relationship. So an object that is witness to a severed relationship may become invalidated, right? So when we talk about an invalid pointer, right, that's a pointer that typically now is not pointing to anything. The thing on the other end disappeared. But we could also say, well, we've got an index to the largest member of this vector. And then we change the value of that largest member. So now it's the smallest member. Now our index is invalidated in the same way that our pointer was invalidated. So relationships are difficult to reason about. And in some sense, they are a more fundamental part of programming than both functions and objects, right? All of the complexity of programming comes about in trying to reason about relationships. And relationships are hard because they just happen. Oftentimes they're just implicit. They're just created. And you make assumptions that they hold, and those assumptions are wrong, and they don't hold. And your code has a contradiction, and it's incorrect, and your program crashes or behaves poorly. Okay? So, how do we do local reasoning about relationships? Well, we have to extract the extrinsic relationships that matter, that are essential to the functioning of our code. Okay, what are those relationships? And we need to encapsulate those into a class and have the class manage those relationships. So the relationships are maintained between parts of the class. If we have two objects that we're going to have involved in a relationship, we want them to be in a class. Okay? It's the interface to that class that maintains the soundness of that relationship. Okay? It makes sure that we don't access something through an invalid relationship. So the class ensures the validity and correctness of the relationships by controlling access to the related objects. So the purpose of a class, you'll often hear, is to protect the invariants of the class. Well, what are invariants? Invariants are relationships. They can be relationships between objects, or they could be other extrinsic relationships, such as just a constraint on a single value, which is a relationship between that value and some other thing. You know, the index has to be 0 or greater. Okay, that's an extrinsic relationship. You want a class to be able to enforce that. Okay. So an intrusive witness. What's an intrusive witness? I've got an object, my widget here, and my widget contains a shared pointer, unique pointer, some kind of pointer to another widget. But that widget isn't considered a part of that widget. What do I mean by it's not a part? If I copy the original widget, it doesn't copy the part. Okay. So I've got a widget. That pointer that's buried in there is intrusive. Okay. That's an intrusive witness. So if I've got an intrusive witness, in my part, then it should only be the owning outside class, right? Whatever it is that contains all of my widgets, okay, that manipulates those relationships. And if I want to extract that part from the whole, then I should explicitly sever that relationship. So if I take my widget out of my, I don't know, my window, maybe it's my window is my whole, I take my widget out of my window, now my widget can no longer reference my window, okay? Or the other widgets that it was connected to. It's a whole, it's extracted, it's out. Okay. So that's how we achieve local reasoning beyond whole part relationships within a class definition. Okay. Now, the interesting thing is, even if you're Mark and you're a functional programmer, okay, the same rules hold in functional programming, right? Right. We tend to think about, well, if we don't have any pointers, if we just have values, then everything gets simple and we don't have to worry about invalidated pointers. But as I pointed out before, just an index can be invalidated. Okay. So I can have relationships between objects in my functional system, which have to be maintained. So what about free relationships? What if I really want to have two objects that are not part of a whole, that are just somehow connected and interact? Okay. So a free relationship is an extrinsic relationship that is not managed between parts of an object. So that's a free relationship. If we assume local reasoning, what meaningful structures can we build? Okay, so what I mean by local reasoning now is we have our object, our class that defines it, and we have a set of rules that that class obeys, and we want to be able to connect other objects to it in an arbitrary way. Okay, what rules does that object have to uphold, and what can we do in that kind of environment? Right. In the probably, mid 80s to mid 90s, this was kind of the panacea of object-oriented programming. We'll just create all these objects, they'll all be garbage collected, we'll just connect them all together, we'll create systems that just work. And they kind of do to some scale, okay? And then you get to the point where you realize that there were other rules on those extrinsic relationships that had to be followed. And now your network is too big and too complex for you to follow those rules. You can't reason about them locally. You had to reason about the system as a whole. You can't do that anymore, and your system starts to collapse. Okay. So, but if we just had local reasoning, could we build things? So this is interesting. There's a paper that came out in 2019 that essentially sets out to answer this. Here's the question asked by the paper. What is the family of problems that can be consistently computed in a distributed fashion without coordination? Okay. And what problems lie outside that family? So that's a link to the paper. It's a good read if you want to go read it. It's a fairly approachable paper as papers go. Okay. And here's the answer the paper comes to. Consistency as logical monotonicity, COM. A program has consistent coordination-free distribution implementation if and only if it is monotonic. Okay. So if people can remember a little bit of math, a monotonic function is a function that's always increasing or always decreasing. Okay. So what happens if you have an object that comes into existence and gets some value and then goes away and then comes into existence again? Okay, that's non-monotonic. That's a non-monotonic pattern. You can't do that and have a system function in an uncoordinated fashion. You have to have some kind of rules that sit on top of that system. So you broke local reasoning. Now you have to reason about the system as a whole. So some examples that fall into COM, CRDTs. People know what CRDTs are? So CRDTs are a collection of data types and algorithms that let you synchronize objects across a network, typically without coordination. And they guarantee that they will eventually settle on the same value. Different CRDTs have different sets of trade-offs on how they reach consistency across the network. Okay, but in essence, they're a monotonic programming pattern in framework. And that's how they function. And kind of a key point of how CRDTs work in a lot of things that fall into the COM category is if you think about a non-monotonic function, okay, you've got something that's going up and down. You can force it to be monotonic by keeping a generation count. Okay, let's say that I cross through 42 twice. If I know this is the first time I crossed through 42 and this is the second time I crossed through 42, I can impose a monotonic function on top of that. And so that's the basic way that CRDTs work, is they impose a monotonic function onto an otherwise non-monotonic pattern. So an immutable variable itself is a monotonic pattern that transitions from being undefined to its final value and never returns. Okay, so immutable variables generalize to immutable data structures. So you can have global variables that are constant, that don't require any additional synchronization. This is why global variables work. Okay, so there are a set of things. Now, the interesting thing is what's the limit? How expressive is a COM programming environment? Well, as far as I know, that's still an open problem. Okay, so like, can you map everything into COM? Maybe. The hypothesis is no, but not proven. Yeah, question.
I have a question.
Sure.
I'm not sure I understand what you mean by monotonic. Monotonic usually implies an ordering
Yes.
less than or equal to. And what is your ordering range?
It is whatever you want it to be. Right?
I don't think so.
Yeah, well, yeah, to be
I'm
monotonic.
trying to prove that it is conflict free or whatever that can be implemented
CRDT.
without, yes, yeah.
Yeah.
Without distributed synchronization. So you must have an idea of what monotonicity is.
Yeah, so
You can't
monotonicity
I
and
define my own relationship and everything is less than something else. It's monotonic and everything that any value that's computed is less than something that came before it or something like that. I can define my own ordering relationship, make it monotonic. I don't think it will work without synchronization. So you better have an idea of what monotonic is.
So
what relationship is it?
right,
Is it
right.
numerical? Is it a numeric ordering?
Well, if you say I've got a monotonic relationship, but the result
That
that I
implies,
expected, but a correct result is
An
not.
ordering.
What's that?
That monotonic implies an ordering.
Yes, monotonic implies an ordering.
What's your,
It always,
what is your ordering?
it always maps to natural numbers, right?
Yeah, well,
that's-
CRDTs do not, CRDTs do not require a total or do not require a total ordering, no.
That's true, but they do
They do require.
a monotonic.
You're talking about programs which compute numerical values only?
What's that?
Are you?
No, but everything maps to that, right?
No, it doesn't.
Yeah.
No, it doesn't.
Yeah, you can, so,
Sounds like the mapping is something the programmer has to do and is not necessarily trivial.
yes.
So
Yes.
you have to arrange it in such a way that you can map your computational state to an increasing sequence.
Right,
What
right,
that means is a very interesting and open question and maybe a lot of work.
right.
No, I don't think so. I disagree with you. Because you could come up with a mapping that is monotonic. Does that imply that every monotonic thing, that's what he seems to be saying, every monotonic computation or whatever, I still don't understand. I'm not grasping the concept. But can it be implemented without synchronization?
I think you have to-
Let me pose a
Yeah.
question.
That's,
Is it possible for a single program to have two different ordering relationships. One is monotonic, one is not. In which case, what? Can it be implemented without synchronization? That's.
I mean, I think
Yeah,
that you'd have to refer to the paper, I'd imagine, that I think the scope of.
I don't think that. I'm asking him for an explanation.
It's right.
Keyboard.
Right. So there has to be a monotonic function that you can map to the computation as a whole. Okay. And when you say, wait, let me finish. When you say it, right, which basically means that you can, map this thing into a sequence of some kind, which is.
That mapping cannot be unique.
What's
can
that?
be many. One can be monotonic, one mapping monotonic, another not. In which case, what?
In which case you can't do anything. You have to map the whole system into a monotonic sequence. Okay.
I come up the same system. I come up with two mappings, one of which is monotonic, one of which is not. In that case, what is your theorem or what is that thing said?
Then you can't do
Map it
it.
into a monotonic sequence, you've got a monotonic. You can map it into a non-monotonic sequence, feel free to hash the same data.
No, they are not equivalent.
They will just be a series.
So, and the result, right? If you're relying on a result that is not a monotonic, it sits outside of your monotonic relation.
Concept of monotonicity because it still sounds very high maybe.
Let's take this one offline.
Let's take this one off. Yeah, I do encourage you, go read the paper. It's a good paper. Okay.
It does not exist.
Okay. So where does this leave us? Well, so interfaces should make the scope of the operation clear. Okay. Projections provide an efficient way to achieve value semantics and manipulate parts. It's the client's responsibility to uphold the law of exclusivity, to make sure that our projections don't overlap under mutation. Okay. The implementer cannot. Okay. So don't pass projections that overlap an in-out argument projection, which is basically what the law of exclusivity says. Implementers should provide types with value semantics, right? So don't provide types that don't have value semantics to your client, right? I always say pointers of any kind shouldn't appear in an interface. Okay, pointers should be an implementation detail. Always, they should be confined in a class. A pointer is always ambiguous. Okay, the semantics of a pointer are always ambiguous.
I have a question about what value semantics means. So you said we should never pass a pointer. What about references? To me, references are like pointers. Maybe we shouldn't pass them, but I don't understand.
Right. We're doing them as projections. Okay. And so we have rules around how we're using them as projections. And even when I say don't pass pointers, there's a little caveat in there, right? A pair of iterators might be a pair of pointers, and I'm treating that as if it were a projection. So if it follows under the rules of treating it as a projection, that's. But if I'm passing a shared pointer to something, a unique pointer to something, that's ambiguous. Okay. Is it a projection? Am I talking about the pointer or the thing pointed to? Okay. And even if you say unique pointer is better than a shared pointer, it is, but it breaks equality. Okay. When I talk about equality of two unique pointers, I'm talking about, are they the same unique pointer? Okay. Because that's the only way that they would be equal, or they're both null. The other way that they are both equal.
recorded audio.
Laptop. Okay. There we go. So my microphone's on, so hopefully people could just read my slide. I'm not gonna reread it from here. So that's the part. If you are in the case where you're like, well, I just want to have a network of objects, you're probably doing network programming. You probably might already be aware of COM. It is a common pattern in network programming, and you might be aware of CRDTs and things like that. But that's the space you're in. There are some things. I should put some more examples in here. If you've got things like a registry, you can say, a registry will follow a monotonic pattern. I doesn't matter what order I put the things in, I can get the things back out. Every client of a registry has sequential consistency. It's a monotonic function. So that's the usual thing. If you're working in multi-threaded programming, you might be a little more concerned about COM and synchronization and how things like that work, especially from an efficiency standpoint, right? How do I communicate between two threads when I have large amounts of complicated data? CRDTs can actually be a useful thing like that, right? How do I take my model of some complicated document and associate it with a UI, which is essentially a different view of the same data, and I want to make sure that they eventually reach consistency, even though they are running independently without synchronization between the two. That would be a good application of a CRDT model to pull that off. If you're familiar with Amdahl's law, there's really good reasons why you don't want to impose the synchronous behavior to ensure that they are consistent between them. Every time you do that, you're going to take a significant performance hit, and the curve is much steeper than you might imagine. Okay. So so being able to reach eventual consistency, even in a non-network environment, is important. And basically, where COM and this monotonicity and things of this nature start to work is it's a function of the latency of your communication. Okay? And what's the cost of synchronization? So that's it for my talk.
Yeah,
sure.
As a question from someone who's ignorant of COM, within the context of the discussion of like immutable objects and monotonicity, would a public ledger on a blockchain be an example of such an immutable object?
That would be an immutable object. That would be a monotonic pattern there.
And what would the numerical, or what would the ordering be in that case? How would you define that?
Well, because it's immutable, you can just say it's forever. There's I'm always appending one more, so it's the count of transactions to the time that it did. Yes. Yes.
Monotonicity really has to do with, a lot of the times that you
What is
have
the value?
a predicate function on something and it is false, and then it becomes true, and it never becomes false again.
Right.
So
So
certainly there is a mapping between, the blocks,
Yeah,
the sequential blocks in the blockchain and the natural numbers, correct? That's monotonically.
No,
Yes,
I think
it's one.
that notion of monotonicity needs to be explained.
I will take that as
more-
feedback to try to provide a better
A
explanation.
little more clear than just saying everything is an integer. That does not explain anything.
Yeah, you have to map it
There
onto
should be
something
some
which is always
more
increasing
detail.
or always
There should be some
decreasing.
more detailed mechanics behind it, make it work.
It's tough for a talk because if I wanted to pull a meaningful example other than saying a global variable, which is a nice trivial example, a registry, I might be able to map it to a registry, which would be okay and show.
Registry, even then, what is
Your
the
messy
mapping?
part of the.
What's that?
Let me, given two states of the registry.
Okay, let's say,
You can't have to come up with two integers. You say everything is an integer. You come up with two integers.
Well,
And what is the order?
okay, so within a registry, first let's define what I mean by this. I put in an object, I get out a token for that object. Okay, so now that the token has gone from a state of not being there to a state of being there. Okay, I can remove it, but the item, the token that I have will never be reused. And so now I have my 0 state is it wasn't there. My 1 state is it is there. I never go back to a 0 state. If I remove it, it is tombstone because the ID for it is never going to be reused. And so now I go back to, that's my 2 state. Okay, so I have 0, 1, 2. Okay, and I can extend that with however many things I want to put in, right? My second thing is then 2.0, 2.1, 2.2, okay, and so on. And now I've got a mapping there of a monotonic function. It's ever increasing, it's never decreasing.
Let me try and understand this.
Okay.
So you're going to identify your possible space of values in your registry could be infinite. They may not be, and each one of them is assigned an index. And somehow each index value gets a value 0, 1, or 2. And that's what you're saying, right?
No.
Yes,
I'm saying
that's
that's
what
the
I'm saying.
mapping. That's the
mapping.
conceptual mapping to the
Please let me
state.
finish.
Yeah.
Please let me finish. So in your registry, when something comes into existence, its value, let's say it has an index of 5. The value of your index 5 goes from 0 to 1. And you have infinitely many indices. And many different things can come into existence at different times. In what sense is that monotonic?
Because-
How would you define the number?
Yeah, I can define the number.
I can give it for you.
Sure, go ahead, Mark.
Everything you're gonna put in the registry, there is a mapping to a unique, positive, well.
That's what I'm saying.
Integer for the things that are in the registry. So we're gonna take,
From 0
we can take.
0 to infinity.
A string, if we're registering strings of characters in, because we're in North America, they're all just 8-bit characters. It's a big number because it's a bunch of bytes, but it's a number and it is unique to that item. That index that is unique to the items that we can register is a bit index into a number that represents membership in the registry. So when we start out the empty registry, it has a value of 0. When we put in the item that has index 5,697,832,452, it sets that 1 bit.
And let me understand that.
And anything you add after that will take the registry's value to a higher number because the bits representing the registry only go from 0 to 1.
Right, just take it to definition. I think
And
that's
if you
the
want to
key.
allow tombstoning, then you
This is
use
a
trinary
relatively
instead
simple
of
example.
binary.
Okay, just a registry. I would be curious as to how would you define that mapping? Or more complicated scenario.
I mean, we could give a
Well-
concrete example with the Bitcoin's public ledger, for example.
No, that's
Bitcoin public
that's
ledger.
That's not a complicated. That's an immutable ledger. It's immutable.
So
By definition.
CRDTs
That's
would
not
be a
complicated.
complicated example,
No,
but that would be a
Let's
2-hour
talk
talk.
about mutable data structures.
What's that? Well, CRDTs are mutable data
Yeah,
structure.
mutable.
Yeah,
Ledgers are not. Bitcoin ledgers are not. So
right,
That's not.
right. So, yeah, but CRDTs would be a 2-hour talk, so.
Standard CRDTs is add-only sets, which is basically what a registry is.
Right,
And the thing that makes them work for distributed computing is that you're
Oh, is that
operation to combine
If
two
that's your
that have
definition,
been calculated in separate points is to union the sets, which forms, I forget whether it's a lattice or a semi-lattice, you know.
If that's your definition, then fine, that sounds believable. Add only sets, add only data structures, not delete.
Yeah, that's why I said the
There
functional data
are,
structures extend.
There should
There
be
are
something more
CRDTs known as
complicated,
OR
it should be that
There are
simple.
CRDTs known as OR SWATs, that allow deletion.
No, that-
And it
I don't-
gets, and that has a trigger
That's where the complexity is
process
likely to
on
come.
it, but
But even our registry example, you know, we said you're allowed to remove the item from the registry. And so in some sense, that's a case where yes, we're allowing a deletion. It's just that we can't ever reuse it. It's either never been there, has been there, or will never be there, or is not there and will never be there again.
3 states, 0, 1, 2. Okay.
there is,
Yeah.
So, tell you what, folks, we got about 20 minutes left before we lose the room. Does anybody have another topic they want to do?
So one thing I wanted to ask is at the beginning of the talk, you showed us that there were 3 different ways of treating parameters.
Yeah.
So there's these parameters that we know are going to be constants, there's these things that are in-outs, there's these reference only. And I was sort of expecting you to say, and what I'm proposing is we add new keywords to C++ so that we can tell when we're looking at each one of these what they are. Now, maybe we can sort of back infer that from types. But
Yeah.
would it be useful or interesting to add some kind of annotations to the language?
Yeah,
To make it
so
easier for the programmer?
the only person who I know who's doing kind of any work in that area is Sean Baxter, who's been he's got his own language called Circle, but it's C++. Okay, and he's been working on basically implementing the equivalent of the Rust borrow checker, but inside of C++ with the C++ syntax. And so he's been adding those keywords. There hasn't been any enthusiasm on the standards committee to kind of go that direction. Our team, I run Adobe Software Technology Lab, and I employ Dave Abrahams, and Dave Abrahams is working on a language called Hilo, which really comes out of Swift, not out of C++. You kind of saw, I saw the Swift law of exclusivity there. In Swift, the law of exclusivity is managed at runtime. And Hilo is, what if we took that and built it into the type system? And it was always at compile time. So that's kind of the 10,000-foot view of what Hilo is. And the difference between Hilo and, say, Rust is that Hilo achieves that by mapping it through whole part relationships, where Rust assumes I've got a bunch of reference semantics stuff, and now I need to have this notion of a borrow checker and lifetime management and things like that. And so you need.
Go ahead and cue your microphone now. This is coming back to life.
see, this is
So where was I? So talking a little bit about Hilo. So yeah, with the idea with Hilo is we're mapping this onto the language. The difference between Hilo and Rust is that by leveraging whole part relationships to control the lifetimes of objects, you end up where you, as a programmer, you don't have to add decorations around to make the borrow checker happy, right? So long as everything falls within the whole part relationship, the compiler can figure it out without additional lifetime decorations. So it comes out of the fact that we think Swift is a simpler programming model, but not as efficient as say Rust, and so locked out of several areas. So the idea is, can we have the Swift simplicity of a programming model, and in some ways even better than Swift, or at least more expressive than Swift. But the efficiency and guarantees that Rust provides. So that's kind of one of the directions we're going. But yeah, I think if you really want this stuff today, to have the compiler enforce it, program in Swift or Rust.
Yeah, so as someone where like to give some as someone whose like knowledge of like correctness of programming is kind of constrained to just the halting problems and not that much. I'm curious about like the applications of like, using this model of program correctness. Would that be applied in like compilers or whatever?
So, yeah, ideally, if you have this capability inside of your language, it provides a certain set of safety guarantees, right? So a safety property is something that's required for your program to be correct and effectively always holds. Okay, so Rust doesn't, unless you use unsafe keyword, Rust doesn't ever let you share mutable references to things. Swift doesn't. Now, as I mentioned, there's all these extrinsic relationships that happen, and that's also part of correctness. And these guarantees don't help you reason about that. It helps, there's within that, there's a set of things you get, but it's not going to help with your assertion that item 5 is the largest value in my set. Okay, that's got nothing to do with mutability and exclusive access control. So safety properties are only one part of proving correctness. And this is only one of a large set of safety properties that you want to have upheld.
You can get your type checker to, depending on your type system, to confirm that you've actually built proper red-black trees and that the balance property holds globally. But that's because the red-black tree properties actually are locally checkable.
Yes. And, if you have a theorem solver in your compiler, like I do some amount of programming in a language called Daphne, which actually comes out of Microsoft Research. Daphne has a set of theorem solvers around it. And so you write the assertions in your code, and then it proves that those assertions are upheld. Now, if you're missing an assertion or your assertion's incorrect, your code's still wrong, but it proves that your code matches what you say your code does.
So follow-up question.
Yeah.
Does the COM paper talk about an automated way to get your ordering? There are an ordering from your program. You feed it a program. Is there a system that I can feed my program to and it comes up with an ordering which is more?
No.
Or is it more like an existence kind of thing?
No.
If there exists a monotonic.
I'm going to interrupt you for a minute. Let's table the monotonic discussion.
Just a short.
Yeah, let's table the monotonic discussion, please. We've got other folks here that have questions.
Yes. And no, it does not provide any such mapping. Like I said, the expressivity is still an open.
It's not just existential. If one exists, then it can be implemented.
Then it can be.
Okay. Other questions, folks?
Is this, do you think this is the biggest sort of like section of C++ foot guns? The reason I'm asking is because like, the reason I'm asking is like if a language were to get this right and be more ergonomic than Rust, do you think that would sort of be the thing where like it starts taking over? Because Rust is in all these other languages think, okay, we got C++ in a corner, we're going to totally take over, and it's kind of happened.
Yeah. Haskell doesn't have any of these problems with Haskell.
Well, right, but I mean, to have like native execution and stuff. I mean,
Haskell has native execution. Haskell compiles to native code.
Yeah. So, if you have this plus lifetime management built into your language, then you have memory safety, and you would even have stronger guarantees than memory safety, and that you would have no race conditions, no data race conditions. You can still have logical race conditions.
Right.
So you would basically get the same guarantees that you had out of Rust. Now, how usable would the language be if this was enforced at some level? That would be interesting, right? A lot of things in the standard libraries quickly fall apart. I mean, even things like how coroutine handles are managed do not fall, in this local reasoning domain, which is very unfortunate.
One of the canonical examples that keeps popping, so I do some embedded, is, you have a DMA engine, right? The minute you've got another piece of hardware reaching in and grabbing things, all bets are off.
Yeah.
It's the aliasing problem in hardware.
Yeah.
Right, so you're done.
Yeah. So, yeah, I mean, to be blunt, I mean, I think C++ will continue to be a very important language, but kind of under the current security pressures. Guidelines, legislation, executive orders, company policies, mandates from Director of Cybersecurity for federal government, EU laws.
The EU laws only apply if you're not a European company, though.
All of these things, I think it is exceedingly difficult for C++ to fit into that framework, which is why you see there's kind of two camps. One is like, well, we can't do anything, so we should just make C++ the best C++ it can be and ignore all of that. And then there are a few people, right? Herb Sutter has an effort for CPP2, and Sean Baxter has Circle, who are taking serious shots at trying to solve it. None of those efforts have any traction whatsoever with the committee. So in that vein, I don't see a long-term path for C++, in the sense that I don't see a long-term path for COBOL either, but COBOL's never going to die, right?
COBOL doesn't have most of these problems.
What's that?
COBOL doesn't have most of these problems, speaking.
Which is true.
I'm a former COBOL person.
Yeah. So, so it's not that C++ will ever die, right? The industry has way too much invested in it. C will never die either, and C is a much less safe language than C++, just in terms of actual exploited code, right? From a language standpoint, C++ is really just as dangerous as C, because you can write pretty much anything in C.
And you can disguise it in C.
You can disguise it, right? Right. So if you're malicious, C++ is a better language to be
Yes.
Or
C++ is more than one. Right.
Yeah. So kind of, it is what it is, right? Day to day, I still do the majority of my development in C++. I'm doing a little bit in Rust. I do a little bit in Hilo as we're bringing Hilo up. I should probably learn more about Swift. But most of what I do in C++ these days is I vet ideas that I want in Hilo.
Okay, we got probably time for one more. We got about 6 minutes before we have to depart.
I'd like your opinion on memory safety. I have fundamental issues trying to understand that phrase. It seems to memory safety means seem at modern day that it is a problem that needs to be fixed. In my opinion, the memory safety refers to something which implies that a language should not allow a programmer, a software developer, to make memory allocation errors, object lifetime, double freeze, stuff like that. All of these are bundled into the term memory safety. In
So-
my opinion, that is a software engineering discipline. And I have never relied on automated memory management. I used to be in the VC++ group
Sure.
whole program optimizations. When memory constrained, I always did my own memory management. I never relied on automated memory management. I did not need memory safety. Sure. I knew as part of my software engineering job to design good, well-functioning software systems is to manage memory. So what do you think of this whole, in my opinion, kind of hoopla about memory safety and all the solutions that have been proposed?
So congratulations on being a very good program. The problem is.
I used to sit in the office next to me.
Right. So the reason why memory safety is an issue is because the Department of Defense was challenged with how do we secure national infrastructure? And what they found is most of the exploitable defects, okay?
Errors.
What's that?
Were due to errors, were they due to?
Well, every exploitable defect is due to a bug.
Yeah.
We can.
There's the first thing is never use the word bug. It is a programmer error.
Okay, it's a bug.
Bugs just got in there.
The largest bucket, if you go and categorize those, of exploitable issues are memory safety issues.
So that's how it came.
So they said, okay, we need to secure national infrastructure. So they go out and they say, okay, nuclear power plant. What software do you use to build this nuclear power plant? They're like, well, we use Linux. We have people drawing diagrams for the control panel in Photoshop. We use a set of open source libraries. We use OpenSSL to communicate between our nodes. We're using this network stack. And what they found is there's no such thing as, critical secure software built in an isolated environment, that all of these organizations rely on a huge amount of open source and software coming from all over. And so it became, well, if we're going to secure national infrastructure, we need to secure the industry. Okay, so a scope creep. So they have rapidly turned it into a consumer liability issue. Yeah. How do we get the scope creep? Well, if your software crashes, you're liable for damages now. Okay, where before you were not. By exception, by law, as one of the few industries in the world, right? If your car crashes because of a defect, Ford is responsible. If your Microsoft Word crashes because of a defect, well, EULA says.
I've got lawyers.
Right. Microsoft is not responsible.
Terms of the end user agreement.
Yeah, Microsoft is not responsible for your lost work because you signed the EULA as a condition of everybody signs it because you don't have a choice. So they're turning this into a product liability issue and to try to move the needle on secure software. So even if you think, well, I write good software, the stats are that the industry doesn't. And the stats are that even with sanitizers and fuzzers and companies like Google that have invested and Microsoft that have invested a huge amount in security and trying to patch all of the defects, they still find like 70 to 80% of their exploitable holes are memory safety issues. Okay. And so, like I'm somebody who would say, well, I don't really need Rust, right? I program like this. I follow all of these rules in my head. And then less than 2 weeks ago, I had a bug in my code where I returned from my functions thinking I'm returning T by value. But T was deduced from a universal reference, which means T could be a reference. So what I intended to say was return to K type T, but I didn't. I said return T. So I ended up returning a reference to a stack variable. Okay, so
Photoshop crashed.
Well, this was in the library code, so no, it wasn't Photoshop crashed, but my library sure did. And it was a pain to hunt down because the code looked correct. Okay. Yes. So.
This is where we get the C versus C++.
It's even when address sanitizer said right here, using a variable on the stack after it's gone, I stared at that for half a day and went like, what are you talking about? Okay.
So, oh,
Yeah. So what do I think about the hoopla? Yeah, it's there's a lot of hyperbole in there. I think it's
Practical reasons.
there are practical reasons for it. There is practical motivation under it. Exactly where it stands, where it's going to fall out, how big of an impact it's going to have on the industry and changing the industry, I don't know. It is clearly changing some things. In my closest analogy is in the early 90s, the Department of Defense said every piece of software we buy or has to be POSIX compliant so that we can run it under any OS. And so Microsoft and Apple made huge investments in getting POSIX compliant. Apple developed their own Unix, and then they ended up partnering with IBM to do AIX, and Microsoft added POSIX support to Windows, and this huge effort. At the end of the day, I don't think having or not having POSIX compliant ever prevented a sale for either company into the military. Because there was always a form to say, I want to run this application. It's only available on Windows. And Windows isn't POSIX compliant. So I need an exception to the rule, exception granted, sale made. Sorry.
Reliability is a more effective hammer.
Reliability.
The way you cover liabilities, you go and you get insurance, and your insurance company says, we don't know anything about software, but we've heard that C++ and C are given to having problems.
Microsoft recently had a huge effort to develop an operating system written in C#, memory safe language. Yes, I don't know what state of life it is in now.
I don't know. You just have to replace Windows with Midori.
Midori, yeah.
Okay.
When I was at Microsoft in 2008, 2009, it's been about a month or two with Midori team. I couldn't figure out how they got themselves funded. But
I was a part of the Phoenix team. Phoenix compiler.
anyway, folks, we're about 2 minutes over, so we need to wrap up and kind of exit so our host can go home for the evening. Thank you, everyone. Thank you.